Hi there. One of the first few days of class, I like to teach opportunity cost and comparative advantage using this activity, squares and triangles. So when students come into class, either the second or third day of class, we launch into this activity without any preparation. So unlike a lot of activities that require some setup, maybe a little bit of reading ahead of time, in this one I really want the students to learn and grasp these concepts simply by what we're doing in class and then by the reflection and debriefing. And this activity is one that I refer back to constantly during the semester. So you can see the first page here. This is a copy of one of my slides. Everyone gets, it says 2 plots of land. I've actually changed that a little bit. Everyone gets a strip of land. The original 2 plots used to be a plot with 2 squares and with 3, but I simplified it a little bit by making this full sheet. Okay, so you can print these off and make copies, and every student gets just a strip like this. And they have to choose whether they want to use their land, their quote-unquote resource, to produce squares or triangles. And then we're going to collect the data from this to create our production possibilities curve. And although the terminology production possibilities frontier, PPF, no longer appears in the College Board course and exam description, students might encounter it somewhere else if they watch online videos or if they take a higher level course in college. So I like to at least introduce that term so they understand that these are the same thing. But then we'll use the term PPC going forward. So I show the students a very deliberate example, how you create a square, which is you simply cut one of these off, right? Now I've turned my resource into a product, which is a square. If I want to create a triangle, right, I have to do the same thing first, but then I simply take my square and I cut it in half. And it's important to explain to the students that if you cut this in half again, right, this does not count as 2 triangles. That is now garbage. Okay, that doesn't count as anything. You cannot produce squares or triangles that are not of a proper size. That would be like saying, well, sure, we can produce a lot of cars as long as we produce them as doll-sized cars, right? We have to produce our products at the size in which our customers want them. So students then have a few minutes with their paper, ideally with scissors, but sometimes we just tear. And then we go around the room and I start asking students, this is of course when I'm still getting to know their names, so I'm calling their names off the seating chart, and I ask them to share with me, what did you produce? And usually the first student will say something like, I did, let's say, 5 squares, right, and no triangles. Because that's sort of the default, right? That's the easiest. You just cut 5 squares, you don't have as much work to do. The next student might say, I did 3 squares, and I have 4 triangles, right? And then I might have someone who got ambitious, right? They did all 10 triangles and 0 squares. And my classes usually have about 35, 36 students, so there's enough of a spread that I get everything. I get every number in this filled in. But if you don't, you can ask the students to come up with what are the other alternatives, right? You could have had 4 squares and 2 triangles. You could have had 2 squares and 6 triangles, or 1 and 8. And you can try this at home and cut out the squares and triangles and see all the possible combinations. And you're going to have some students who are going to ask questions like, which one's more valuable? Which one do consumers want? You can't answer that question. I just tell them, well, maybe I'll tell you later. So they kind of, have to make up their mind about what they're going to do without knowing what they can sell it for. But it's a great question, right, to think about, because we come back to that later from the producer's perspective. I would certainly spend my time producing squares, right, if they sold for more than twice the price of triangles. But if they don't, then maybe I invest in producing triangles instead. So then we use this very simple exercise to calculate our opportunity cost per square. So if we have 0 squares, right, we're down here at point F. We have 0 squares and 10 triangles, and I want to know what is the opportunity cost of the first square. The students come up with that pretty quickly. It doesn't take much instruction, right? I just ask them, what's the opportunity cost of the first square? And they say 2 triangles, right? So to move from point F to point E, right, in order to get my first square, I must give up 2 triangles. So the opportunity cost of a square is 2 triangles. What if I'm at E and I want an additional square? Well, again, I have to give up 2 triangles, right? This carries on all the way. If I'm at B and I want to get to A, I've got 4 squares and 2 triangles, but I just want 1 more square, got to give up 2 more triangles. So all the way along, right? The opportunity cost of a square is always 2 triangles. So what is the opportunity cost of a triangle? Most students pretty quickly realize it's half a square. Some of them want to argue, though, well, you had to give up a whole square, right? In order to get a triangle from this, you have to give up a whole square. And that's where I like to kind of jump to the relevant real-world comparison and point out that, sure, that is true in this case. However, if I were farming and I decided that I wanted to shift over, I wanted half an acre of corn, I don't have to give up a whole acre of soybeans to get half an acre of corn. I can have half an acre of soybeans still and half an acre of corn. So in this case, I can have a triangle and I can have a leftover half square, right? So that's the way I want them to think about it. The opportunity cost of a triangle is going to be 1/2 square. And again, that's going to be true whether we're going from A to B, right, or from B to C. Every time if we move from A to B, in order to get those first 2 triangles, we have to give up 1 square. So to get 1 triangle, we only have to go halfway, right? And at that midpoint between 0 and 2, we would have 4.5 squares and we would have 1 triangle. So we would give up 1/2 of a square. So this is a nice way to get them thinking about opportunity cost in a very simplified fashion. And then you can take this data and the students can individually graph it. In my case, I have the students graph on shared whiteboards. They can go through and very easily, again, with little instruction from me, they figure out that, here's the points, and they're actually better than I am about making their points accurate and linear. I'm always kind of throwing this together because I don't have a grid on here. Right? And I also don't have a straight edge, so I'm just going to connect them as best I can. Okay, and that is my production possibilities curve. And we can see the same thing on here. If we want to have 1 unit of squares, right, if we're up here at 10 triangles, want 1 unit of squares, we have to give up 2, right? Move from 10 to 8, we give up 2 triangles to get 1 square. If we're here, we have 5 squares and we only want 1 triangle, right? We have to give up, in order to get to that 1, we have to give up half a square, right, to get 1 triangle. So this is a case of constant opportunity cost. Now, we can look at a few other things while we have this curve here, too. I can throw questions at them like, well, which point on this graph is better? This is point F, right, and this is point A, and we have B, this is point C. Is point C preferable, or point A, or point F? And we want to make the point that we can't necessarily tell just from looking at a production possibilities curve, right? Especially one that doesn't involve the trade-off of consumer and capital goods. This, where it's just 2 consumer goods, there's no way to tell which point is preferred by consumers. We can also throw in other points like point G, right, and point H, and ask the students, can you produce at point G? And they realize, no, I can't because I'm limited by resources, right? So that point is unattainable because we have too few resources. Later on, the kids are going to try to say things like, well, if we were more efficient, we could produce at point G. And you can remind them, without more paper, right? The best scissors, the best paper cutter in the world, the fastest cutting, none of it's going to get you to point G. You need resources. Okay, point H, there's going to be some kid in class who doesn't produce anything or produces very few, right? That is possible. It's attainable. But it's undesirable because it is inefficient, right? That is not an efficient use of resources. But every point along the graph is an efficient use of resources. So this is attainable but inefficient. Okay, and then there's an additional part to this, which I will give you the handout so you can read about it. But there's an additional part to this lesson where you can actually enlist some student volunteers and demonstrate increasing opportunity costs instead of constant ones. And you do this by having a few volunteers of ranging height, right? And the tallest student, you give them the ability to pick either 5 units of apples or 1 unit of carrots. The middle-sized student, 3 units of apples, 1 unit of carrots. And then your most height-challenged student, 1 unit of apples or 1 unit of carrots. And you see what happens if all 3 of them spend their time and their resources picking apples or if all three of them spend their time and resources picking carrots, and then you see what happens as you shift people over in production. So it's a nice way to illustrate increasing opportunity costs as well. And both of these activities let students have a really hands-on grasp of how to calculate opportunity cost and what a PPC represents.